this is how we could look at an RL circuit. This is a resistor inductor circuit. So in general, what we have here is we have some sort of EMF, we have a resistor, we have an inductor. That's what we've got. Okay. If we look at this circuit, the EMF here is going to be driving a current this way. That's the current, thanks to the EMF. Now, our inductor is actually going to do something interesting. As this change of a current processes through, like we flick the switch on, it is going to try to drive an EMF backwards. Okay, and by that, that current is going to try to shift back. What we're going to do here is we're going to see how an RL circuit operates with a Kirchhoff loop. Everybody's favorite. Okay. Kirchhoff loop. If we set up the Kirchhoff loop of this, and let's set it walking around just like this, kind of in the direction of our primary current, what we're going to see is we're going to gain an EMF in the beginning because we're going across the terminals in the positive direction. When we go across the resistor, we're going to get minus IR. And then this is the tricky one. When we go across the inductor, we know that this inductor is going to have an EMF given by L didt. And if we remember, this was technically in the equation as a negative value. Okay? Well, the negative value we've already used. The negative value, whenever that popped up, that negative was actually that this EMF is going to be generated backwards. So what we can actually do is we can think about this inductor in terms of a Kirchhoff loop like this. If we pretend that it wasn't an inductor, but it was an EMF generator. Well, if the EMF is generated backwards here, then that means that this EMF is actually big and little. That's the direction this EMF is trying to generate. And then looking at that, that's an easy thing for the Kirchhoff loop to set up. It's minus EL. And then we're back home. That's equal to 0. Okay? So that's an interesting way you can think about the inductor if you're having problems setting up like a Kirchhoff loop or something. Just think of it as a flipped battery to what you're going for, or an EMF. Okay? Rewriting this, we can see that we're going to have epsilon IR minus, and then here's our L didt. And we don't get the minus of the minus from the equation because we've set up the circuit correctly itself. Okay? I'm going to rewrite this just so that it reads L didt plus IR equals epsilon, the EMF. Okay, so I just shifted everything so everything's positive. This is our standard LR circuit equation. Okay? What you can do is you could show, using a little bit of knowledge and a little bit of calculus, that the current moving through this system as a function of time is actually going to be equal to epsilon over R times the quantity 1 minus e to the minus t over tau L, where tau L is equal to L over R. This is the inductor time constant. And it's very, very similar to how you did this for a capacitor. So if you're watching this video, you can pause it here, see if you can solve this, okay? What you should be trying to do is try to get didt right here. Try to get it by itself. If you can do that, then you're pretty much home free to move forward, okay? So pause the video, take a few minutes, see if you can get that by itself, see if you can derive this equation to show what we have here in green, and then unpause it and come on back, okay? You got 5 minutes. See how far you can get. And we're back. Okay, so let's derive this sucker. You don't get better at this unless you tried it. So if you just are still listening to me and you didn't pause the video, didn't try it, what the heck? If you want to do well in school, you got to put the sweat into it. Okay. We've got the equation. I'm going to just rewrite it again. IR plus L di dt equals epsilon. And if you have these different, who cares? It's just adding, doesn't matter. Okay. Let's first, to get di dt by itself, because that's our main objective, let's pull IR over. Okay, so we're going to have here is we're going to have L di dt equals epsilon minus IR. Okay, so that's where we're at right now. Our next move here, in order to get di dt by itself, is divide by L. Divide by L, divide by L, divide by L. Rewriting that, and we're going to do a lot of rewriting here, so just get used to it. We're going to have di dt equals epsilon over L minus IR over L. Okay, if you got that far, you did great. You set up the differential so that you can go ahead and solve it. Okay, that was all the legwork right there. So, ta-da, you did it. Way to go. Okay, this here, this is the trick. This is the trick. From this point, what we're trying to do is we're trying to separate the variables. We are trying to get di and I together on the same side of the equation with the di in the numerator. At the same time, we're trying to get dt to be in the numerator. So naturally, it's going to have to move over here. And then since there are no other t terms here, we can just lump stuff with it. We can lump constants with it, so that's fine. Okay? To do this, what I'm actually going to do is I am going to, this is kind of a trick here if you've never seen it, I am going to multiply everything on this right-hand side by 1 over r divided by 1 over r. And distribute that sucker. And that seems like completely, what? Why did he do that, right? Well, we need to recognize that 1 over r times 1 over r, this equals 1. So I haven't done anything. Multiplying something by 1 is, you haven't done anything there, okay? But what I have done is if I rewrite this, I've kind of set something up for me to use. di dt, like always, equals, well, I'm going to have epsilon over r over L over r minus I r over r, so now that r is going to go away from the I, divided by L over r. So this is kind of nice because what I'm going to see here is that these are going to go away. My denominators are still the same, so everything can still link together. If I rewrite this and clean it up a little bit, because it's always nice to clean stuff up as you're doing the math, we get di by dt equals epsilon over r over L over r minus I over L over r. Whew. Okay. From here, we can finally start moving things around and making life a little bit nicer. Okay, I am going to take this entire numerator term and I'm going to divide by it on each side. So it's going to cancel itself out over here and we're going to find it in the denominator over here. I'm going to take dt and multiply it on both sides, so it's going to cancel itself out over here, and then it's going to wind up in the numerator over here. Okay? So when I do that, what I'm going to get is I'm going to get di divided by epsilon over r minus I equals dt over L over R. Okay? And if you got this far, then, like, holy cow, way to go. Because you have just set everything up so that from here, there's one little step of calculus to do, and then it's just clean up in the world of algebra. Okay? So if you've gotten this far, you've done everything right. You get this time to just do one move of calculus. Okay? The calculus move we're going to do here is we're going to integrate. If you're not entirely familiar with integration, check out the integration videos I've got up here, or check out Wes Baker's integration stuff, or Khan Academy's got a little bit of stuff from integration, or just wait for Cotton to get to that, because she'll get to it. But we're going to integrate both sides here because we've got this di and this dt term. Okay. When I integrate these sides, I need to set up some bounds for the integral. And this is kind of it's not really a nuanced thing, but it's something you kind of get used to doing. For my time, we're starting from time of the initial. Okay, so like t naught, but often we just call the initial time 0. That's when you start your watch. So we're going to go from a time 0 to some arbitrary time later. Let's just call it t. For our current side of things, we're going to have something similar. At the initial time, our current is 0. It hasn't started to flow in the system yet. But at some later time, we have some current I as a function of t. Now, technically it is a current I of t, but we're going to save that of t to the end. Let's just save some space and just call it current as a function of I. Okay, so we're going to some later current I. So, this integral on the right, this is a fairly basic integral. L and R are constants, so they get pulled out here. So they're just going to stay like that. And we're actually just going to be taking the integral of dt. When you do that, the integral of dt, bounded from 0 to t, is actually just going to give us t over L over R. Ta-da! There it was. That was the integral. Okay, nothing crazy. Something we can actually do, though, to clean up a little bit, because we're going to see this pop up, and we're going to see, if we scroll way back, this here, L over R, this time constant for an inductor. Let's use it. Okay, let's replace this L over R here with tau L. Okay, so that's the integration of dt. As for our left side here, we need to be a little careful. If we look at the left side, this is actually going to be a u substitution, and if we're clever and we kind of look at this, we know it's going to be a natural log because we've got di over some I. But if we set up our u substitution, our u is going to be, in this case, e over r minus I, and our du is going to be then negative di. And I don't have a negative di here. I have a positive one. So one of the things you could do is you could put the negative here, and then you say, okay, if I put the negative on this side, that means I have a negative over here, which means that this negative carries through. That's one way to do that. Okay. What I am going to do, which is a little bit different, is I'm essentially going to multiply each side by -1. So I am going to get the negative here, which brings this negative down here with the integral, okay, because it's just a constant -1, which carries through. But instead of dealing with this negative here and having to deal with that the rest of eternity, what I'm going to do is I'm going to swap places down here. By doing this, I'm essentially multiplying by -1. I'm distributing that through. So what I'm going to get in this denominator is I actually now have, after I've made this little move, I actually have I minus epsilon over R. Okay, so that was the little switch move I did there. By doing this, whenever I have my u du set up, what I'm going to have is my u is going to be I minus epsilon over R, and the derivative of that with respect to I is just going to be di, which I have. So this integral essentially boils down to be du over u. You know that's going to be a natural log of u. Technically, Will's probably going to yell at me about this because that's an absolute value there. Okay, but whatever. Math's the math class to yell at you for that. Okay. In the end, though, what we're going to get here is the natural log of, and then our u quantity. This is going to be I minus epsilon over r, and then since we actually have our I here, this is going to be what the heck? I minus epsilon over r minus our lower bound. Our lower bound here is when I equals 0. If I equals 0 there, then we're going to have here the natural log of negative epsilon over r. Okay? And you've done it. That is what it is. At this point, it's just some math cleanup. There is some special rule in math where when you subtract logs, you're actually dividing them. That's a thing, apparently. You should remember that, hopefully. So we're actually going to have the natural log of I minus epsilon over r over negative epsilon over r equals negative t over tau L. And then from that, I don't like to deal with this negative here. So I'm going to pull a little trick move in order to flip things back. So I'm just going to rewrite this as the natural log of epsilon over r minus I over epsilon over r. If you're like, hey, Coach Botz, I don't like to do that. I like to leave the negative and then move it out later, or whatever. You're playing algebra, okay? So that's kind of how that's going to pan out there. To get rid of this natural log, exponentiate each side. Okay, and at this point I'm kind of moving because I'm basically done. I see the light. E to the minus t over tau L. And then I can make a few little quick plays here. What I'm going to do is I'm going to rewrite this side right here as 1 minus I over epsilon over r equals e to the minus t over tau L. And then I'm going to add this term over and then subtract this one over. So I'm going to get 1 minus e to the minus t over tau L equals I over epsilon over r. And then the very last move to make things complete, I'm going to take epsilon over r and multiply it over. And it's multiplied by the term, so this is actually going to become the current as a function of time equals epsilon over r times the quantity, 1 minus e to the minus t over tau L, where tau L equals L over r. Fin. Hey bots, I won't be in class tomorrow.